So what we've done up till now is we've talked about adding an acid to water or adding a base to water. And so there's particular sorts of equations that we've written where the acid reacts with a water molecule or the base reacts with the water molecule. What we want to move on to now is looking at reactions between an acid molecule and a base molecule, right? Not reacting them with water, but reacting them with a base. So hydrochloric acid reacting with sodium hydroxide or reacting with ammonia or something like that, right? And we're going to do it in this context of something called a titration, which is a way of measuring what the concentration of one of these things is. So let's imagine that we've got a solution of hydrochloric acid and we're going to mix it with a solution of sodium hydroxide. Right? Two flasks, one with hydrochloric acid in it, one with sodium hydroxide in it, and we're going to mix those together. The equation that we could write to describe the reaction would be like this. We could write HCl aqueous plus NaOH aqueous gives Cl minus aqueous and Na plus aqueous, so chloride ions and sodium ions and water. And we could write that, and that would be okay. But we also know from what we've already talked about today that if you have HClAq, what that really just means is H3O plus ions and chloride ions, because the HCl completely reacts with the water to make H3O plus and Cl minus. And if we write NaOH aqueous, then we know that sodium hydroxide, when you put it in water, will completely dissociate to give sodium ions and hydroxide ions. So instead of writing HClAq and NaOH AQ, we could simplify the equation, take out the spectator ions that you learnt about in the lab the other day, and we would be left with an equation that looks like this. The H3O plus, which comes from the HCl, plus the OH minus, which comes from the sodium hydroxide, reacts to make two lots of water. Right? So no sodium ions in there and no chloride ions in there because they're spectators. They don't do anything. Never think that you should be writing Na plus or Cl minus being a reactant somehow in an acid-base reaction. Right? If you have sodium cations, the only thing sodium cations can do is they can get an electron from somewhere and turn into sodium metal, but if they do that in water, it will promptly explode and take your hand off. Right? And you'll notice if that happens. It doesn't happen. Right? We're going to talk about those sorts of reactions at the end of the week. But in acid-base reactions, the sodiums and the chlorides are always spectators. And so we can simplify this equation down to this, right? One H3O plus reacts with one OH minus to give two lots of water. And note that this reaction goes to completion because we're reacting a strong acid with a strong base, right? So we write this with an arrow, a one-way arrow, this equation. We're going to see other ways of doing this shortly. So we could just take a beaker with the hydrochloric acid solution and a beaker with the sodium hydroxide and mix them together, and then the reaction would happen. But instead we're going to do it in a slightly different way. Let's imagine that we start with a conical flask and we put into it 25 mils of our acid solution. Right? We can get a pipette and we can carefully pipette 25 mils of our HCl solution into this little flask. And then let's imagine what we're going to do is rather than just pour the sodium hydroxide in and be done with it, we're going to slowly drip it in. And as we slowly drip the hydrochloric acid, the sodium hydroxide in, we're going to measure the pH of our acid solution in the flask. Right? So initially that pH is going to be much less than 7 because it's an acid solution, right? And as we add the sodium hydroxide to it, we're going to see how the pH changes when that reaction happens. Yeah? You would expect, hopefully, that the pH should go up. Yeah? But does it go up in a straight line? Does it go up in a parabola? Or what does it do? Well, this is the sort of curve that you get, right? And these curves are on your handout, so you don't need to just scribble them all down. So here is our flask. And in our flask, we have our hydrochloric acid, our strong acid, right? And so we initially somehow measure the pH in here, and we could do that by bits of paper, or we could do that by putting a pH meter into that solution, a little instrument that can measure pH. And here's the pH down here, right? It's about 0.8. And then what we do is up in here, we have this thing called a burette, which is just like a big long test tube with a tap on the bottom. And in here, we have our sodium hydroxide solution. And when we open this tap, the sodium hydroxide will slowly drip into our acid. And that chemical reaction that we wrote the equation before for, H3O plus OH minus gives 2 lots of water, that chemical reaction starts. Whenever you add hydroxide into here, it will immediately react with that acid. That reaction will go to completion, and you'll turn the acid into water. And the hydroxide you add will also turn into water molecules. Yeah? And so as you do that, the concentration of H3O plus in here goes down because it's a reactant in that reaction. And so if the concentration of the H3O plus goes down, the pH of the solution should go up. Yeah? And so it does. But it doesn't go in a straight line. It goes in this interesting curve. And so it slowly curves its way up and up and up and up, and then all of a sudden it starts changing very, very quickly until you get to this point S. And which we're going to talk about, and then it keeps going up and up and up and up, and then it curves gracefully over at the top and then eventually flattens out up there. Right? So it's not a straight line, it's an interesting curve. So this point down here is before we've added any of our sodium hydroxide solution. And so the pH down here, you could calculate. If you knew the concentration of the HCl solution, you now know how to calculate the pH at that point in that curve, right? Way up the end, this is where, if you like, we've added 14 litres of sodium hydroxide to the solution. So now it's basically all just sodium hydroxide, right? And so the pH out the end will be basically just the pH of the sodium hydroxide solution that you've been adding. And you can calculate that as well now. You can take that concentration of OH minus ions, convert that to a POH, and from that you can work out the pH. Right? So you've got the math now, and you've got the formulas to work out the pH here and the pH at the end. In fact, for this titration in theory, you now know enough to work out the pH at every point in that entire curve. We're not going to make you do that today, I don't think. But we're okay with those? We're happy with this bit? Yeah? Okay. So then, we worry about point S, right? So this is S. And if you like, S is halfway up this really steep part. If you're into calculus, anyone into calculus? Yeah? If you took the first derivative of this curve, it would be the maximum in the first derivative of the curve. Yeah? The point of inflection, blah, 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 blah. We don't do calculus in my class. So it's the halfway up the steep part, yeah? Point S is the point where we've added enough sodium hydroxide to completely react with all of the acid that was initially in your flask. All right, so there's a certain amount of HCl that was originally there. Point S is when we've added that same amount of sodium hydroxide. And that will also be the point where all of the hydrochloric acid has reacted because of that one-to-one balancing in the equation, right? And this is where we keep it easy. You could make it 2-to-1 here, but then it just gets horribly complicated. So if you know the amount of hydrochloric acid that you start with, then this point S, which is called the equivalence point, is when you've added the same amount of sodium hydroxide. So all of the hydrochloric acid has now reacted. And so now what we can do is we can think about what's in our little flask when we reach point S in our titration, in our experiment, where we slowly add the hydroxide to the acid. At that point, is there any hydrochloric acid in your solution? Yes, says one person. Do people agree? Oh, come on, someone say something.
There never was any HCl, so it was aqueous.
Outstanding. Very good answer. Is there any H3O plus that came from the HCl left at point S? Yes. No, is the answer. Because at that point, by definition, it's when all of the H3O plus that came from the HCl is gone. Right? We've added enough hydroxide ions for all of the H3O plus to have reacted and be gone. Right? Is there any hydroxide ions from the sodium hydroxide present at point S? No, because every time you add a drop of sodium hydroxide, all of that sodium hydroxide reacts with the acid and disappears. So all the way up to here, all of the hydroxide that you're adding immediately reacts and disappears and turns into water. And all the way up through here, the concentration of H3O plus from your hydrochloric acid is getting less and less and less and less and less until at this point it gets to 0. Yeah? So at that point then, all we have in our solution is the spectator ions, the sodium ions and the chloride ions, which weren't doing anything anyway, and water molecules. And so this point S, the equivalence point of your titration, when all of the hydrochloric acid, or the H3O plus that came from the hydrochloric acid, and all of the hydroxide ions have reacted, at that point the pH will be 7. We happy with that? Because even though you started with an acid solution and you're adding a strong base solution to it, those are reacting with each other and turning each other into water. And when that reaction happens completely, all that's left is water and your spectator ions. So here's the reaction. And so at point S, all you've got left is these things. I'm a very big fan for titrations of having people thinking about what's going on in the little flask. Right? It's very easy to just memorize these curves and go, oh, that's that and that's that and that's that. But if I have anything to do with it, we will ask you interesting questions to see whether you really understand what's going on in the solution when you do one of these things, right? Rather than just mindlessly memorizing stuff. So I'm going to be very keen that you understand what's going on in the little flask. And we're going to come back to this a lot tomorrow as well. Okay, so that's if you start with the hydrochloric acid in your little flask and you add the sodium hydroxide to it out of the burette, as it's called. Yeah? You can do it the other way around. And if you do it the other way around, then you get the same sort of curve, only it's upside down, which is probably what you would expect, right? So if you start with your sodium hydroxide in the little flask and you add the acid to it, you add the hydrochloric acid to it, then the pH starts off being very high because you've got a very basic solution, and then the pH slowly comes down as the hydroxide ions get turned into water, right? So the concentration of hydroxide comes down, so the concentration of H3O plus must go up, because remember those things are always related by that pH plus pOH equals 14 thing. So if the concentration of hydroxide ions comes down in your solution, then the concentration of H3O plus must go up, and so that works out as the pH coming down. Right? You might want to think through that one a little bit. Yeah?
Does the equivalent of change be depending on the strength of the reactants used?
If it's a strong acid reacting with a strong base, then no. Because they're all strong acids. So regardless of whether you start with HCl or HBr or HNO3, when you put it in water, all you've got is H3O plus. Right? What you're alluding to is what we're going to do is titrations with weak acids. And then different weak acids are differently able to give away protons, and then it does, yes. We're still getting to that. I think that's tomorrow. Right? If you're titrating a strong acid with a strong base, then the equivalence point pH is always 7, regardless of which strong acid and strong base you use, and regardless of which one's in the little flask and which one's in the burette. It's always 7. Yeah? So now let's imagine that instead of having a strong acid in our little flask, we have a weak acid. So acetic acid, say. We've still got a strong base in our burette, but we've got a weak acid in the little flask. Then the shape of the curve is a little bit different. Again, it's going to start here, and the pH here, this value A, will correspond just to the pH of our weak acid solution. So you can work that out now. We just did that before. How if we said it was 0.024 moles per litre acetic acid in here, you could work out what the pH is of that acid. When you then add the strong base, the sodium hydroxide, say, then it becomes a little bit different. Because in the previous curve, as you'll see in your handouts, this pretty much just goes along and straight up. Now it goes up for a bit, and then it flattens out for a while, and then it goes up again. The equivalence point is still the same in that it's the point where we've added enough strong base to exactly use up all of the weak acid that was in our flask. But the pH of the equivalence point is going to be different now. It's not going to be 7. Because the things that are in our flask at the equivalence point are not just the spectator ions and water. There's more going on in the flask than just that. And that we're going to get to tomorrow. But in this case, you can see that the pH of the equivalence point is actually about 8.2. Yeah.
But why are the curves the shape they are?
Why are they curves?
Why are the curves flat?
Why does it go flat and then up? Tomorrow. The next thing says the flat region is called the buffer region. More of this tomorrow. The reason why the curves at all rather than straight lines is because we're measuring pH, which is a log thing. Right? Obviously, if we were just measuring the concentration of H3O+, then it would be a different shape. But because we're measuring pH, and the pH we get by doing logs, that's what gives these things these interesting curves. So initially, it's the same. You just work out the pH just by doing the calculation. And at the equivalence point, it's still the place where we've added enough strong base to react with all of the weak acid that was initially there. But in between times, it's a little bit different when you've got a weak acid. And we're going to deal with that a lot more tomorrow.